In the previous video, we talked about a local version of isodiametric inequality. We drew a lot of pictures explaining why a global version is never possible, and also some intricate questions and geometries that come up with such inequality. Already there I promised that I will give a metric version of that, which also is more general in other senses, and that is the topic of this video. I will put the previous video at the end of this one so that you can see also in the links in the description of the video. Okay, so what was the whole question about? The question was, given a set, can we bound its Hausdorff measure by simply the diameter of the set to power s? Because that's how the Hausdorff measures are defined, and also when s is equal to n, the dimension of the ambient space, such inequality is indeed true for all sets. The best that probably can be done was if you have a set with finite s Hausdorff measure, then at almost every point there is some delta x where if you look at sets of that scale, then up to this error epsilon, which is arbitrary, you can indeed have the isodiametric inequality. The precise statement is that whenever you have a closed ball near x, which is quantified by this requirement that x belong to B, not necessarily the center though, and the diameter is less than delta x epsilon, then the intersection of that ball with our set, which could be seen as an intrinsic ball in the space x equal a. If we ignore Rn and we consider A as a metric space, then this is just a ball in that relative topology. Then yes, so this is true. That was the theorem. Now, in our paper with Piotr Hajlasz, we proved that in any metric space in general, you have a similar result, but our result is probably better because we get this inequality not for just intersection with ball, but just any set that is contained in the ball. And in a second, I will explain why this is not a trivial consequence of the previous one, or at least I didn't find a way of obtaining this 2.8 from the previous version. The reason I'm mentioning also this paper is because there is a full proof of that result in there as well. So this was published in Annals Finici Mathematici. I hope I'm reading it the right way. And yeah, so the full proof with all details is contained there. Now, if I compare them, so the stronger inequality is saying that as long as you have f contained in this closed ball centered at x diameter delta x, of course this delta x could be a different delta x by a factor, say 2. But the point is, here I again have diameter of f. Here you can take this to be your set f, and indeed any set near x can be written in this form, but the problem is then you have diameter of the ball and not diameter of f. Now you would be able to go from that inequality to this if you know the following, that is every f of the form B intersection with A for some ball with diameter of B equal to diameter of F. So is every f of the form, or is a subset of a set of this form? It will also work. And this is not true in general. Not every set can be contained in a ball of equal diameter. And if you haven't seen this at first, it seems surprising, but the answer is actually very simple. I mean, the example is simple. You take an isosceles triangle, rather just the vertices of it. So these are at equal distance from one another. So for example, you can say this is 1, which makes all these mutual distances 2. Now, if you want to take a ball of diameter 2, so diameter of this set, which consists of the 3 points, you could add the edges for free. It wouldn't change the analysis. So the diameter is 2. If you take a ball of diameter 2, then, and if it contains x1 and x2, then it must have this segment as its diameter. That means the center of the ball must be here. Okay, there I go. So I got lucky a bit, getting the perfect circle once I cheat. Now necessarily this third point will not be in that ball. And because of symmetry, if you do with x2 and x3, you run into the same issue. So there does not exist a ball which contains f with diameter of b equal to diameter of f. Of course, if you allow squaring, I mean, doubling the diameter, definitely this is always possible in any metric space. In Euclidean space, probably you can reduce that factor by less. Maybe there's always a ball with diameter equal to root 2 or root n in n dimension times diameter of the set you want to contain in a ball. But anyway, we don't want to pay any price at all. So the whole point is really getting here as close to 1 as we want, and here paying any price is just not acceptable. So in that sense, it is not trivial, at least I didn't find a way, please let me know if you do, of obtaining this result. This would be for every f contained in x delta x with, I don't think you need to say diameter is less than something because it's already contained in this inclusion. Anyway, so I don't see any way to obtain the second one from the first one, and that's why the result in the paper is somehow stronger. Yeah, so this is my second and last video on this topic of local almost isometric inequalities, almost because it's 1 plus epsilon and not 1. Hopefully you will find this video also helpful, and please remember to subscribe, that still matters on this end, and see you in future video. Thank you and have a good one.